Good afternoon, dear children. We can continue the lesson oscillations. Okay. Last class we have discussed about the energy of a particle that executing simple harmonic motions, where we have derived the equations for kinetic energy and potential energy, and also we calculated the total energy of a particle that executes simple harmonic motion. Also we have drawn a graph that relates the energy, the variation of energy with the time. Listen it. And today's class we are going to discuss about the horizontal oscillations of a body on a spring. Horizontal oscillations of a body on a spring. Actually here we are going to prove that the horizontal oscillations of a loaded spring is an example how it actually it is an example for simple harmonic motion. That is, the loaded oscillations of a spring is simple harmonic motion. That thing we have to prove. Okay, the horizontal oscillations of a loaded spring. The horizontal oscillations of a loaded spring is simple harmonic motion. For that, we are consider a spring. Okay, consider a massless spring which is lying on a horizontal table, and one end is actually attached to a rigid support. One end of the spring is attached to a rigid support, and the other end is end a body of mass m. The other end is attached to a body of mass m. Okay, actually this is the condition for equilibrium position of the spring. That is, here we are not applying any force. So F equal to 0. So actually it is the equilibrium condition. Next we are pulling the body, okay, through a small distance of x. Listen, next what we are going to do is we have to pulling the body through a small distance of x, okay, and then released. If you pulled and released, so it starts oscillating horizontally, okay, it starts oscillating back and forth. Okay, when we pull this mass to one end and then released, it will starts to oscillate back and forth about the mean position or about the equilibrium position under the action of the restoring force F equal to minus kx. Restoring force we have already learned. Okay, actually this spring execute oscillation, or the loaded spring that execute horizontal oscillations under the action of the restoring force F equal to what? Minus kx. Okay, here we are considering a body of considering a massless spring lying on a frictionless horizontal table, and its one end is attached to a rigid support and the other end to a body of mass m, isn't it? And if the body is pulled to its right through a small distance of x and released, then it executes it starts oscillating back and forth about a mean position or a equilibrium position under the action of the restoring force F equal to minus kx. So we can write the force F equal to what? Minus kx, where k is the force constant. I think you know where k is the force constant, and the negative sign indicates that the force and the displacement are opposite direction. The negative sign indicates that the force and displacement are in opposite direction. And suppose if A is the acceleration produced on the body, then by Newton's second law we can write F is equal to what? M into A. Let it equation number 1 and this is equation number 2. Let A is the acceleration produced on the body, then by Newton's second law we can write F equal to ma. Then we can equate these two. Ma equal to what? Minus kx. Ma equal to minus kx and A is equal to minus k by m into x. This m comes here. Okay, k A equal to what? K by m into x. Listen it here. Instead of k by m we can write what? Minus omega square x. So acceleration A is equal to minus omega square x. So actually this is the equation for simple harmonic motion. Acceleration of simple harmonic motion. Acceleration of a particle that execute what? Simple harmonic motion. A equal to minus omega square x. Also we can write A proportional to what? So A proportional to what? X. Okay, acceleration A proportional to x. And this essentially indicates that the loaded horizontal oscillations of a loaded spring is the about the simple harmonic motion. Okay, here the acceleration is proportional to the displacement. That means this here the spring execute what? Simple harmonic motion. Okay, also this is the equation of the acceleration of a particle that execute what simple harmonic motion. This again confirms the horizontal oscillation of a body on a spring is an example for what? Simple harmonic motion. Okay, also we can find the period of oscillation, time period t is what is equation for time period t? That is 2 pi by omega. Time period is equal to 2 pi by omega. And here, k by m equal to what? Actually, omega square. K by m equal to omega square. From this, omega is equal to what? Root of k by m. So, we got omega as root of k by m. That thing we can substitute here. That is equal to 2 pi divided by root of k by m. And this thing can be written as 2 pi into root of m by k. This is the equation of period of oscillation of a loaded spring. 2 pi into root of m by k. Okay, t equal to 2 pi into root of m by k. Listen to it. Here, it oscillates under the action of the restoring force. The spring or the body gets oscillated under the action of the restoring force. So we can write the restoring force F equal to minus kx. Suppose if A is the acceleration produced on the body, then we can write by Newton's second F equal to ma. Then we can equate this to ma equal to minus kx. From this A equal to minus k by m into x. But we know the value of k by m as omega square. So we can write A equal to minus omega square x, or A proportional to x. Actually, this is the condition for a motion becomes what? Simple harmonic motion. Okay, so we can conclude that the horizontal oscillations of a loaded spring is essentially a simple harmonic motion. Next, we can find the period of oscillation. For that, we are considering the equation for time period t is equal to 2 pi by omega. Then, if we have to substitute for omega, for that we are considering k by m equal to omega square. From this, omega equal to root of k by m. Then we can substitute 2 pi divided by root of k by m, and this thing can be written as 2 pi into root of m by k. 2 pi into root of m by k. This is the period of oscillation of the loaded spring. Okay. Next topic is simple pendulum. Okay. Here also we have to prove that the oscillation of a simple pendulum is simple harmonic motion, and also we have to find the period of oscillation of simple pendulum. Period of oscillation of simple pendulum. Actually simple pendulum consists of a bob. It consists of a metallic bob. Actually, it is attached to the end of a light and inextensible string. Okay, simple pendulum consists of a metallic bob, and it is attached to the end of a light and inextensible string. Okay, when the bob is displaced to one end and released, it executes what? Oscillation. Okay, actually it executes simple harmonic motion. That thing we have to prove. Okay, a simple pendulum actually consists of a bob attached to the end of a light inextensible string. When the bob is displaced to one end and released, it executes what? Simple harmonic motion. That is the bob that moves to and fro. Okay, actually let m be, we are considering let m be the mass of the bob, and the L represents the length of the pendulum. Okay, m represents the mass of the bob and the L represents the length of the pendulum. Okay, here let the bob be displaced from the mean position or from the equilibrium position. A, here actually the mean position is A or the equilibrium position is A, to the position B through a very small angle theta. Okay, listen to it. The bob is displaced from the equilibrium position to the position B through a small angle what? Theta. Listen to it. Let the bob to be displaced from the equilibrium or the mean position A to a position B through a small angle theta. Okay. Here the force due to the weight of the bob, the force due to the weight of the bob mg, that is acting vertically downward. Okay, the force due to the weight of the bob, that is actually acting vertically downward, and this mg that can be resolved into two rectangular components. Okay, the mg that can be resolved into two rectangular components. One is actually mg cos theta that acts along OB. Okay, here the mg cos theta that acts along OB, and another is the mg sin theta which acts along BA through the tangent. Okay, another component is actually mg sin theta that acts along BA along the tangent of BA. Okay, here the weight of the bob that is acting vertically downward, that is actually mg. This mg can be resolved into two rectangular components. One is mg cos theta which acts along OB, that is mg cos theta, and another is mg sin theta which acts along the tangent of BA, which acts along the tangent of BA. Isn't it? And here the component mg cos theta that balances the tension T that produced in the spring. Okay, we are adding actually due to the weight of the bob, the string gets stretched. So somewhat. So force, that is tension produced in the spring, that is actually T. So the component mg cos theta that balances the tension T produced in the string, that is T, can be written as mg cos theta. T can be written as what? Mg cos theta. And here the component mg sin theta, that is actually towards the mean position, that is the restoring force. Okay, the restoring force is actually always towards the mean position. So the restoring force F equal to what? Mg sin theta. Okay, F equal to what? Mg sin theta. Suppose if theta is very small, then sin theta can be approximately equal to theta. Okay, if we consider theta as very small, the angle theta is very small, then sin theta can be approximately equal to what? Theta. So this equation becomes F equal to mg theta. Okay, F equal to what? Mg theta. Here also we are putting in negatives and restoring force, minus mg sin theta, go minus mg theta. Isn't it? But what is theta? Theta can be written as this theta is equal to this arc length divided by this. Actually, this arc is a part of circle. So this arc length divided by this much distance, that is the radius of the circle. Okay. So theta can be written as this x by l, arc length divided by radius. This theta can be written as this arc length x divided by the radius l. Isn't it? So we can substitute F equal to minus mg. Instead of theta we can write x by l. Okay. Okay, F equal to minus mg x by l. Isn't it? And here under the action of the restoring force, the bob execute oscillations, and so the acceleration produced on the bob, acceleration A is equal to F by m. The acceleration produced on the bob, A equal to what? F divided by m. So that is equal to, F is actually minus mg x by l divided by m, and this cancel, and we got minus g by l into x. So the acceleration A is equal to minus g by l into x. Isn't it? You know that the length of the pendulum and acceleration due to gravity, that is constant. So the acceleration is proportional to what? The displacement x. The acceleration is proportional to the displacement x. That is the condition for the motion of particle or the oscillation of a particle to become simple harmonic. So from this we can confirm, okay, or we can conclude that the oscillation of simple pendulum is essentially simple harmonic motion, because acceleration is proportional to displacement. Acceleration is proportional to what? Displacement. Isn't it? Here the weight of the bob that is acting vertically downward, that is mg. This mg can be resolved into two rectangular components, mg cos theta acting along OB, then mg sin theta which acts along the tangential of BA. Listen it. And here the component mg cos theta that balances the tension T produced in the string, that is T can be written as mg cos theta, and this mg sin theta, the restoring force is always acts towards the mean position. So mg sin theta is the restoring force. So F can be written as minus mg sin theta, or F is equal to, suppose if theta is very small, then we can write sin theta approximately equal to theta. Then instead of sin theta we can just write theta. So we got minus mg theta. And next we have to substitute for theta. Here actually x represents the arc length and let L be the radius. Then instead of theta we can write x by L. Then substitute for theta as x by L, F equal to minus mg x by L. And under the action of the restoring force, the bob execute oscillations about the mean position with acceleration a. So the acceleration produced on the bob A is equal to F divided by M, and here the F is minus mg x divided by L, that whole divided by M. This M cancel and we got acceleration as minus g by L into x. G and L are constants that you know, so the acceleration is proportional to displacement x. From this we can, this is the condition for a motion to become simple harmonic motion. Acceleration is proportional to displacement. From this we can conclude that the oscillation of a simple pendulum is an example for is essentially a simple harmonic motion, isn't it? Next we have to find the period of oscillation of simple pendulum. Okay, period of oscillation of simple pendulum. Okay, here we have the relation for acceleration E is equal to minus g by L into x. We can compare this with the standard equation of simple harmonic motion. Acceleration of simple harmonic motion, that thing minus omega square x. This is the standard form, A equal to minus omega square x, and here we have acceleration A is equal to minus g by L into x. Then instead of omega square, in the place of omega square, here we have g by L. So omega square equal to g by L, then omega equal to square root of g by L. Okay, omega equal to what? The square root of g by L. Then what is omega? 2 pi by t. Omega is actually 2 pi by t. 2 pi by t equal to root of g by L. Root of g by L. But we have to find what the t. So we can cross multiply. T is equal to 2 pi into root of L by g. That is the equation for period of oscillation of what? Simple pendulum. T is equal to 2 pi into root of L by g. Okay. To find the period of oscillation, we are considering the acceleration A of the simple pendulum is A equal to minus g by L into x. That is actually the acceleration. A equal to minus g by L into x. Here we are comparing this acceleration with the standard acceleration of a particle that execute what? Simple harmonic motion. That is A equal to minus omega square x. That is the standard equation. A equal to minus omega square x. Then in the place of omega square, here we have g by L. So omega square equal to g by L. From this omega equal to root of g by L. But omega equal to what? 2 pi by t. So instead of omega, we can LHS we can write 2 pi by t. So 2 pi by t is equal to root of g by L. From this t equal to what? 2 pi into root of L by g. 2 pi into root of L by g. That is the period of oscillation of a simple pendulum. That is the equation for period of oscillation of a simple pendulum is that is t equal to 2 pi into root of L by g. Next about free oscillations and damped oscillations. Okay, free oscillations and damped oscillations. These free oscillations are otherwise called undamped oscillations. Okay, free oscillations are otherwise called what? Undamped oscillations. Suppose if a body oscillates with a constant amplitude, that is the amplitude which does not change with time, such oscillations are called free oscillations or undamped oscillations. Okay, here we can see that the body that oscillates with a constant amplitude. Here there is no change in the amplitude. That means the amplitude remains the same. Okay, the amplitude remains a constant. Such oscillations are called free oscillations or undamped oscillations. Okay, the energy of an oscillating system that execute undamped oscillations remains the same. Okay, and it is independent of time. Okay, the energy of this system that execute the free oscillations or undamped oscillations that remains constant or remains the same and independent of time. That is why the amplitude remains a constant. Okay, and such oscillations are called what? Free oscillations or undamped oscillations. Suppose if the body execute or the body oscillates with a constant amplitude, that which does not change with the time. Such oscillations are called free oscillations or undamped oscillation. This represents what? Free oscillations or undamped oscillations. So for example, the vibrations of prongs of tuning fork struck against a rubber pad. That is an example for free oscillations. Okay, the vibrations of prongs of tuning fork when struck against a rubber pad. Okay, also the vibrations of strings of sitar when pulled aside and released. That is an example for free oscillations. The vibrations of the strings of sitar when pulled aside and then released. Also the vibrations of or the oscillations of bob of pendulum are examples for what? The free oscillations or undamped oscillations. Listen to it. Next about what? Damped oscillations. Damped oscillations, that is the amplitude that gradually decreases with the time. Here the amplitude is not a constant which decreases, it goes on decreasing, the amplitude goes on decreasing with the time. That is what the damped oscillations. The amplitude is not a constant. Here the amplitude of the vibrating particle that goes on decreasing with the time. Such oscillations are called what? Damped oscillations. Okay, actually in most of the oscillations, the part of energy of the oscillating system actually that oscillating system that lost to overcome the resistive forces such as what? Frictional force and viscous force. Okay, the energy, a part of energy of the oscillating system is lost in order to overcome the resistive forces like frictional force and viscous force. That is why the amplitude goes on decreasing and finally it becomes zero. Such oscillations are called damped oscillations. Listen to this. Suppose if a mass suspended by a spring gets vibrated inside a liquid, where that is an example for damped oscillation, or the oscillations of swing in air. This is an example for what? Damped oscillations. Okay, here in the case of free oscillation, the amplitude remains constant with it as time passes, but in the case of damped oscillation, the amplitude goes on decreasing with the time. Okay, that is the difference between free oscillations and damped oscillations. Next about forced oscillation. Next about what? Forced oscillation. Suppose if the oscillation is under the action or under the influence of an external periodic force, external periodic force, then the particle vibrates not with its natural frequency but with the frequency of the external forces. Such oscillations are called forced oscillation. We can consider an example. Okay, first, suppose if the stem of the vibrating tuning fork, the stem of the vibrating tuning fork is pressed against a table, we can hear a loud sound. Suppose when we press the stem of a vibrating tuning fork against a table, we can hear a loud sound. Actually, this is because the particles of the table are forced to vibrate with the frequency of the tuning fork. Okay, here the particles are non-vibrating with its own natural frequency. Instead of that, the particles vibrate with the frequency of the external force. Here the external force is the vibrating tuning fork. So the particles of the table are forced to vibrate with the frequency of the tuning fork. Okay, that is why these oscillations are called the forced oscillations. Okay, suppose when the stem of a vibrating tuning fork is pressed against a table, we can hear a loud sound. What is the reason here? This is because the particles of the table are forced to vibrate with the frequency of the tuning fork. Actually, it is not vibrate with the frequency of the particle itself. Okay, the particle has certain natural frequency. But here the particles are forced to vibrate with the frequency of what? Tuning fork. That is why it is called the forced oscillations. Okay, so the oscillations under the influence of an external periodic force, then the vibrating particle is not vibrated with the natural frequency of its own, but with the frequency of the external periodic force. Such oscillations are called the forced oscillations. Okay, what is meant by forced oscillations? If the oscillations are And suppose if the oscillations are under the influence of an external periodic force, the particles vibrates not with the frequency of frequency of its own, but with the frequency of the external periodic force. Such oscillations are called what? Forced oscillations. Okay, that is about what? Forced oscillations. Next about resonant oscillations. Okay. Actually, it is a particular case of forced oscillations. Okay. Actually, in this, the frequency of the external periodic force or the frequency of the driving force. Okay, that external periodic force is actually called the driving force. Okay, the frequency of the external driving force is equal to the natural frequency of the oscillator itself, and the amplitude of oscillation becomes very high, and such oscillations are called the resonant oscillations. Okay, actually it is a particular case of forced oscillations in which the frequency of the driving force become equal to the natural frequency of the oscillator itself, so that the amplitude becomes very high, and such oscillations are called resonant oscillations. For example, an aircraft passing near a building actually shatters its window panes. Okay, an aircraft passing near a building shatters its window panes if the natural frequency of the window matches the frequency of the sound wave sent by the aircraft engine. Okay, so that we can hear a loud sound. Listen to it. An aircraft passing near a building shatters its window panes if the natural frequency of the actually it shatters the window panes. What is the condition that shatters the window panes? The natural frequency of the window matches with the sound waves sent by the aircraft engine. Okay, that is the condition for about example for resonant oscillations. Okay, actually it is a particular case of forced oscillations in which actually the frequency of the driving force is equal to the natural frequency of the oscillator itself, and the amplitude of oscillations becomes very high. Such oscillations are called the resonant oscillations, and such phenomenon is called the resonance. That is the frequency of the driving force that matches the natural frequency of the oscillator itself. That phenomenon is actually called the resonance, and a particular frequency this will happen. Okay, that is at a certain frequency alone, this frequency of the driving force matches with the frequency of the oscillator itself. Actually, that frequency is called the resonant frequency. Okay, that is the frequency at which the resonance happened. That frequency is called what? Resonant frequency. Okay, that is about what? The resonant oscillations. It is a particular case of forced oscillations in which the frequency of the driving force is equal to the natural frequency of the oscillator itself. Okay, and the amplitude becomes very large. This type of oscillations are called the resonant oscillations. Okay, children, that is about what? Resonant oscillations. Okay, so today's class actually we have discussed about the horizontal oscillations of loaded spring, where we have calculated the period of oscillation T as 2 pi root of m by k. Then also we have proved that the simple pendulum that oscillates simple harmonically, and also we have derived the expression for time period of simple pendulum, that is t equal to pi root of L by g. And also we have discussed about damped and undamped oscillations. Next came forced oscillations, and also we have discussed about resonant oscillations and the phenomenon resonance. Okay, children, that is the end of today's class. Also we have finished that lesson. Okay, thank you.